Welcome to the massive open online course on Aspen Plus. In today's lecture, we are going to discuss about filters. Filtration device is something which filters out the liquid from a suspension or slurry and separates the solid from it. In general, the process of filtration is used in our everyday life, from the morning tea to purification of drinking water and many other things. But today we are going to discuss about the filtration devices that are used in the chemical industry. You might have remembered the type of filtration devices that we have learned in our undergraduate days. In the mechanical operation laboratory, we have done experiment on press and frame filter or rotary drum filter. Okay. So today we are going to discuss about such industrial type filters, how they are used in Aspen Plus domain, what are the parameters or what are the data inputs that we have to feed in order for the Aspen Plus to work for filtration device. First, we will go through some theory and then we will solve the problem as usual. Let us first go to the Aspen Plus simulation window and let us see what kind of filtration devices are available in Aspen Plus domain. So in Aspen Plus, the filter is available in the solid separator model palette over here. So this is the filter. So filter block, if we keep it over here, so these are the mandatory inputs that we have. This is the mandatory feed. This is required. Okay. So let us call it feed. And then this is the solids. Obviously, the filtration is a process by which we separate the solid from the liquid. So let us name it as solid. And this one is liquid. Okay, so these are two mandatory streams. One mandatory input and two mandatory outputs. One solid, one liquid. And there are additional inlets, maximum 2 inlets and maximum 2 outlets. Now, these inlets and outlets are useful for certain types of filtration device that we will learn later. For the time being, we are not connecting it. We will connect it as and when it is required. Now, if you go to the block and see input, so these are the specifications we have to provide while working for filtration device. First of all, we have to fix the model. There are 4 types of models available with which we can work with filtration device. First one is solid separator. Now, this is common for all the solid separators that we have used so far, like cyclone, scrubber, centrifuge. For everything, we have a solid separator model. And this is same for everything. So we are not going to learn anything new over here. We can skip it. Other than the solid separator, there are 3 types of models that are available for the filtration block: drum, belt, and disc. Let us understand what they are. For that, let us go to the Aspen Plus help file. Here you will find all the filter references that are available over here. So you can go through each one of them to understand better for filtration references. First, we will see what is a drum filter. Now, drum filter is same as the rotary drum filter that we have learned in our undergraduate days. Now, this is a schematic of a rotary drum filter. Now, from the laboratory experiment that you have done in your undergraduate lab, you can recall to some extent how it looks like. It's a hollow cylinder with a perforated cylindrical surface. So this entire surface of this cylinder is perforated. And this entire cylindrical surface is also covered with a filter cloth. This is the slurry zone where the suspension of solid particle in a liquid is kept, which needs to be filtered basically. And a portion of the cylinder is submerged in the suspension. This entire cylinder is under vacuum, and this cylinder rotates very slowly around its axis. So there will be a rotation like this. So while this portion is submerged into the liquid and the cylinder is under vacuum, the liquid infiltrates. Due to the vacuum, liquid infiltrates through the filter cloth as well as the perforations. While the solid material, they cannot infiltrate and they remain on the cloth and they form some cake. As the time progresses, more and more solid deposits on the surface and the cake becomes thicker and thicker. So, as the rotation happens, the entire surface of the cylinder is covered with the cake. This portion is obviously the filtration zone where the filtration occurs, and this portion is deliquoring zone. Deliquoring means demoisturizing of cake, because once the filtration happens, the cake forms, but the cake will also have some moisture in it. Cake will not be dry, right? In this deliquoring zone, no more filtration is occurring, but liquid will be sucked by the vacuum inside the cylinder and the cake will become dry. Then comes washing zone. Washing zone is required where the extra amount of liquid is poured onto the cake so that any kind of contamination can be removed. So this is the washing zone. And again, due to washing, the cake will again become wet and moisturized. So the second deliquoring zone is over here, whereby the extra amount of washing liquid that has gone to the cake, they can be removed from there. So this is the second deliquoring. And once the cake reaches over here, we have a scraper. And this scraper will scrape the solid from the surface so that the surface is regenerated. And it is needed because there are two types of resistance to the filtration. Number one is filter cloth. Filter cloth, anyway, it will present a constant resistance to any filtration. But additional resistance will be provided by the filter cake, because gradually the filter cake will be thicker and thicker. Once the filter cake gets thicker, it will pose extra amount of resistance to the filtration. So in order to remove that, we have to put a scraper over here. So the job of the scraper is to scrape the solid and separate it from the device. Okay, so this portion is regenerated, filter cloth, so that the filtration can be realized once again over the filtration tube. So that is the entire filtration operation while the rotary drum filter rotates and all these things happen. And these are few important parameters of device geometry which are either to be specified or they are to be calculated or designed by Aspen Plus. For instance, drum diameter, drum length. So drum diameter and drum length, if it is a simulation case, then we have to provide and simulate. And if we have to design them, then Aspen Plus will design the drum diameter and drum length based on other requirement that we have posed. Then the drum speed, at which speed the drum rotates. Then immersion length. So this is the immersion length. Obviously, you can see how much it is immersed. The drum is immersed inside the pool of slurry. And the angles of deliquoring filtration over here, angle of washing, this is the angle of washing, and then angle of deliquoring. Angle of deliquoring is this one. This one and this one, both are angle of deliquoring, and this is angle of deliquoring filtration. Again, angle of filtration is there, angle of cake formation is there. Okay, so all these angles you need to specify as and when required. And here are some typical geometry and process range. For instance, the drum length will be between 1 to 6.5 meter. Drum diameter will be between 0.5 to 4 meter. Drum speed will be 0.2 to 5 RPM. So this is normal. It is a very slowly moving process. Then total area, angle of filtration, angle of washing, angle of deliquoring, applied vacuum, how much vacuum has to be applied for good filtration. Okay, how many number of segments, cake height. So cake height should be at least 5 millimeter for the scraping to happen, and it should not go beyond 40 millimeter because so filtration cannot proceed beyond that cake height. So this is about vacuum drum filter. Next is disc type of filter. Now disc type of filter in general is similar to rotary drum filter, but there is some difference. We'll discuss about that. Now disc filters consist of several filter discs arranged on a hollow shaft. That means there will be some flat disc of this nature. There will be a hollow disc. They are hollow disc like this. Hollow disc with flat surfaces. Okay? And many such hollow discs with flat surfaces will be there, and they will be stacked, and one common shaft will axially connect them. So that's what it means. And in contrast to the vacuum drum filters, where the shell of the filter drum realize the filtration, the flat face of the disc is responsible for the separation process in case of disc filters. So here in the rotary drum filter, we had a cylindrical surface for the filtration to realize, but here this is a flat surface, this is the flat surface, this is the flat surface, this is the flat surface. So on these flat surfaces, the filtration occurs. Okay, that's what it is. It also has the same angle of filtration, angle of deliquoring. Okay, and these are angle of segment. Now this disc is not a single piece of entity. Rather, these discs are maintained with some segments. So this is one segment, this is another segment, this is another segment. Like that, all the segments are combined together to make a disc type filter. Okay. So working principle of disc type filter is same as the rotary drum filter. Once these segments are submerged into the liquid, the filtration is realized. Once they come out, then washing, deliquoring, etc. that happens. And it also has deliquoring angle, filtration angle, washing angle, etc. And there is some extra angle which is called dead zone, which is the angle between filtration and deliquoring. And dead zone 2 is the angle between deliquoring and filtration. So between these two angles, no filtration or no deliquoring occurs. So this is the dead zone. Likewise, we have geometry and process range for this type filter. So diameter of the disc, it is between 0.5 to 5 meter, whereas the number of segments are 6 to 20 to 36. Number of discs is 1 to 15. Total area, disc speed, applied vacuum. Now these things are quite similar to the rotary drum filter. In the case of rotary drum filter also, we have seen the rotating speed is less than 5 rpm or so. Applied vacuum is also in the same range. Okay, cake height also is 5 to 40 millimeter. And one more difference that we observe over here about the scraping, how the scraping occurs. In drum filter, we had the scraper over here, but in disc type filter, suppose this is the side view of the disc, it looks like this. Okay, so scraper will be somewhere here. At both the sides, the scraper will be there. So this is the axis. As the disc rotates, the scraper will scrap and the solid will fall over here. Okay, so there will be a solid collector over here. So this might be a bit confusing because you have not probably come across this kind of disc type filter in your undergraduate laboratory. So I will show you a small animation video where you will see how it works. It will clarify your doubts. So let us go to the animation video and see how it works. This disc type filter is from Enriched company. You can see how they have been made. And all the discs they're connected through an axial pipe, which is under vacuum. And you can see the segments. See how the feeding is done. So as the filtration occurs, the cake is formed, and there the cake is being scraped. You can see how it is being scraped. There is a scraper, blue colored scraper. You can see the location of scraper in the small inside video. This is a piping arrangement. And for all the segments individually, they are showing. And how they change the filter cloth. So one by one, they remove the individual segment, remove the filter bag, and insert a new filter bag and put it back. And fix it with screws. So that is how the disc type filter works. And the third one is the belt type filter. Now the belt type filter, as the name suggests, you will find a belt over here, and this belt is perforated, and the filter cloth will also be there on the belt. The belt will move like this. Through the roller, it will rotate like this. This is the suspension filtration zone where the slurry will be put and the filtration will happen. This is the washing zone. There are two washing zones shown over here. And this is the deliquoring zone. Okay. And in this kind of system, we have to provide some airflow also into the system so that the cake is dried and it can be scraped over here. So this is the point where the cake is scraped. So this is the journey of the suspension. So it is poured over here, gets filtered, it is washed over here, then it is deliquored. By the time it reaches over here, it is comparatively free of moisture and it is thus scraped. So this is belt filter in general. Now, many of you might not have seen the belt filters in the undergraduate lab. So I have got a animation video of belt filters. So let us watch that animation video and learn it better, how it works. So this is also Enrich company belt filter. So you can see how the slurry is fed onto the belt. And they are washed. And as it reaches over there, it becomes dry. And belt rotates and comes over there. And wash spray is given on the belt and its cloth. The filtrate is taken out through those pipes. Here you see how the air cushion is given. So basically air is flown over there. So I hope you have understood how belt filter works. Now let us choose drum, and no matter whether you use drum type or belt type or disc type, in all of them you have two modes of operation. One is simulation, another is design. In simulation mode, you have to provide this information like drum diameter, drum width, drum speed, filtration pressure drop, deliquoring pressure drop. These are the information that you have to provide for the Aspen to simulate your device. But if you intend to design it, in that case, this information will not be required. The information rather, what is the cake saturation content? What will be the cake thickness? So those are the type of information that you have to give to Aspen Plus so that Aspen Plus back calculates and tells you what should be the design parameters like the drum diameter, drum width, which will arrive you at a cake thickness of that much or cake saturation point of that much. Okay, so that is the difference between the calculation mode, simulation or design. Then we have the filtration model. How we want to do our calculation through which model. So there are four types of filtration model available: general, Holditch, Alice, and Brownwell. Now we will go one by one. First is general type of model. For that, you can go over here. So this is the general filtration model. The general filtration model is based on the Darcy equation. You might be very much familiar with the Darcy equation of filtration model. And in this equation, the liquid flows through the porous medium and it is physically modeled. In analogy to the electric resistance, the liquid flow depends upon the potential force, that is the pressure difference, and a resistance. So this is the resistance. Okay. Over here, there are two types of resistance. One is resistance due to the filter media, and another is the resistance due to the cake formation. Because the resistance due to the filter media is constant. It depends upon the thickness of the filter cloth. It will not change. The filter cloth thickness will never change. But the cake thickness changes. So when the cake is thin, then the resistance due to the cake formation will not be high. But if it is quite a thick cake that has formed onto the filter surface, then it will give an extra amount of resistance to the flow of filtrate across the filter media. So these are the two resistances we work with. Vf is the volumetric flow of the filtrate, that is the liquid that infiltrates through the filter medium. Delta P, this is the pressure drop across the filter media. A is the area of filtration, eta is the viscosity, and then RC, area specific cake resistance, and Ks is constant in general filtration law depending on feed suspension properties. So these are the things which are required for the general filtration model to calculate. So from this general filtration equation, you have to arrive at this Vf. Okay, so Vf is the constant pressure filtration model. Okay, this Vf. Now, Vf is obtained by integrating this dvdf dt. Okay, although it is quite straightforward, but I just wanted to give you a hint how you can yourself do the derivation. Let us assume that the portion within this square bracket is denoted by x. So this is x is equal to the portion within the square bracket. Then dx dt is equal to RCKS by A into dVf dt. RFM is constant, the resistance due to the filter medium, this is constant. So dx dt is equal to this into dvdf. Now we go back to the original equation. This is the original equation. So dvdf dt is equal to this, which can be written as, instead of dvf dt, we can write A by RCKS into dx dt is equal to delta P into A by eta into x. Instead of this one, we write x. Now take x this side, dt this side, and integrate both sides, and we get x square by 2 is equal to the entire thing into t plus c, the constant of integration. Now we have to find the c, constant of integration. At time t is equal to 0, obviously, initially there is no filtrate. Okay, Vf is also 0. So c is equal to xt square by 2 is equal to half of Rfm whole square. So put this over there. So 1 by 2 x squared. So this is the x square is equal to this plus Rfm square by 2. And just do the rearrangement, algebraic rearrangement of the equation, and you will find the final form Vf is equal to this, which is same as this one. Okay, so that is how the derivation is done. If you want to find the mean filtrate flow of a continuous filter, then this is the mean filtrate flow. You will find a term Tz over here, which is the residence time of the filtration zone. That's how you calculate the volumetric flow of the filter. So this is the general filtration model, and while calculating it, you have to provide the drum diameter, drum width that will calculate the area of filtration, number of segment, drum speed. Based on the drum speed, the extent of thickness will also be calculated. Then filtration angle, filtration deliquoring angle, filtration pressure drop, deliquoring pressure drop, filter medium resistance, all those things you have to provide. And in deliquoring, there will be two types of model, Schubert model and Nikolov. So this is about general model. Then come to say Brownell model. Brownell model, you can see we do not have to provide much information. So Brownell model, if you see over here, Brownell filtration model is the original model for filter in Aspen Plus. So when Aspen Plus was first introduced, it used to use a very basic type of filtration model. So Brownell filtration model it first used. Later, it got complicated and other models have been included in the software. So this is the original model for filtration. And this model does not include the calculation of washing and deliquoring. Okay, it is just filtration and that's all. And this Brownell model assumes the cake thickness to be around 6.35 millimeter. It should be greater than that. The capillary number is greater than 1 and filter cake is incompressible. We'll come to the incompressible and compressible cakes a bit later. For the time being, it is enough for us to understand the volumetric flow rate of filtrate that can be calculated from this equation. In fact, Aspen Plus uses this equation to calculate through Brownell filtration model. Then comes the Alice filtration model. Now, Alice filtration model, it is formulated using a partial integral differential equation for the compressible cake filtration problem. In the last two cases, we didn't consider the cake to be compressible. But in Alice filtration model, we assume the cake to be compressible, and this is the formulation. Okay, here we have the PS, that is the pressure on the solid, and WS, it is the coordinate due to the cake compression. So we have to solve it and find out this VF. Okay, so ultimately finding out the VF is important because it is a partial differential equation and it has the integration over here. So first we have to assume some specific volumetric flow rate. On that assumption, we calculate the boundary conditions of filter media and calculate the structure data of one layer of cake thickness. And if we reach the cake surface after the calculation, then it is okay. Otherwise, we go back and do the calculation once again. Once we reach the cake surface, then we see whether the condition of specific volumetric flow rate is met or not. If that condition is fulfilled, then it's okay. Otherwise, we'll go back and assume something else as the specific volumetric flow rate. So once this condition is fulfilled, we have to calculate the suspension and clear fluid data, safe data, and we have to see whether the conditions for ending calculation is fulfilled. If it is fulfilled, it's okay. Otherwise, we have to go back and restart the calculations. So this is a kind of trial and error method, a repetitive method. Usually for solving any kind of partial differential equation, we come across this kind of situation. So this is nothing new for the calculation to happen. So this is the algorithm for Carina Alice for modeling the cake filtration. So you can go to this reference if you want to learn it further. And it's a German thesis rather. That's what we have it over here. And then Holditch filtration model. Holditch filtration model makes it possible to calculate compressible cake filtration in more detail. Okay, And this is the total pressure difference in the filtration. Here also we have the VF that needs to be calculated. And as I said that it calculates the compressible cake filtration in more detail, you see how these calculations are done. Three methods are given. First one is incompressible cake method. It is general. Okay. Sometimes it is incompressible cake method. So Kozeny-Karman equation can be used. Kozeny-Karman equation, we are very familiar with Kozeny-Karman equation because we have learned Kozeny-Karman equation when we studied the packed bed type of column. So chemical engineers are very familiar with it. But there are two compressible cake methods, method A and method B. So you can check, say we use Holditch model. If we choose compressible A, there are two options, mean value and local value. And we have to specify this Ka, Na, Ke, Ne. These parameters are useful for fixing the simple power function of porosity. So this is the porosity and simple power function of mass specific cake resistance. Here, either the mean value or the local values are calculated. For that, we have to specify Ka, Na for the cake resistance and Ke, Ne for the porosity to calculate these simple power functions, either mean value or local. So based on which one we use, we have to select accordingly and specify the values of it. Then comes the deliquoring model. Deliquoring model, there are two types of deliquoring model. One is Schubert, another is Nicolau. So Schubert model, you can refer over here. Basically, we have to find out the value of S. And S is the saturation. Okay. S res is residual saturation. S infinity is equilibrium saturation. That means saturation as it reaches when time t is equal to in. So we have to calculate this saturation in deliquoring model. And for that, the parameter n is important. And we have to fix the parameter n, Schubert n. Residual saturation is calculated from this equation where we need n cap. N cap, that is capillary number, is also calculated from this. So all these information are there in the system with Aspen Plus. So n cap and S res will be calculated by Aspen Plus itself. We have to just give the value of n. So n cap will be calculated, S res will be calculated, K will be calculated from S res. Only n, that n parameter we have to provide. And once we provide the parameter n, Schubert model will calculate St. And constant n ranges from 2 to 4. From literature, it has been found. And the other one is Nicolau deliquoring model. It is almost the same principle. Instead of residual saturation, we have the equilibrium saturation in this case. Similarly, we have to find out the K value for here, and we need three parameters. Nicolau, the moment you choose Nicolau, these three will be activated. So Nicolau A, Nicolau B, Nicolau C. Here you will have A, B, and C. So if you provide these three information, then ST will be calculated. The saturation of deliquoring model will be calculated. And there are two models for washing. Now, washing is not activated. For some factors, the washing will be activated. Okay, we will see this washing model when we'll solve the problem. Okay, For the time being, let us understand two types of washing model. One is Choudhury and Dahlstrom. Another is dispersion washing model. Now, in Choudhury and Dahlstrom washing model, we have a washing ratio. This washing ratio is VWL by epsilon V cake. VWL is volume of washing liquid. V cake is the volume of cake and epsilon is the porosity. So epsilon multiplied by volume of the cake, that will be the entire pore volume of the cake, right? Now you find another ratio C by C naught. C is the mass concentration of the contaminants of the cake after washing, and C naught is the concentration before washing. Now suppose washing ratio is 0. That means there is no VWL. If there is no washing liquid, then NW will be 0. And if NW will be 0, then what will be C? C will be equal to C naught because there will be no washing at all. So C by C naught is 1. And as you increase the VWL, the ratio becomes more and more. That means more and more washing liquid will be given into the cake and the washing will happen. And after some time, you will find the C, that is the concentration after washing, it becomes very, very less because you have provided lot of water for washing and it has washed out all the contaminants from the cake. So that's exactly the principle of Choudhury and Dahlstrom. Similarly, you have dispersion washing model. Here also you have C, and this model is a bit complicated because you have error function over here. If you're interested, you can go to this particular literature and you will find sufficient information about the dispersion washing model. Now let us solve an example problem to understand the principle of filters better.